Hello, my name is Chaewon Park, and today I'll be presenting the LFI-CAM paper, which is Learning Feature Importance for Better Visual Explanation. I'd like to thank my co-authors Hong-Yi Lee, Jung Yeon-oh, and No-Jung Kwak for their contribution to the paper. On a high level, this paper proposes the LFI-CAM model, which overcomes numerous limitations that conventional CAM variants still possess, and achieves stellar performance on both classification task accuracy, attention map quality, and stability over different hyperparameters. We leveraged various techniques such as attention mechanism and devised a new internal network module called Feature Importance Network. From related works, we discovered through extensive experiments that attention branch network, aka ABN, outputs unreliable and inconsistent attention maps when experimented with various hyperparameters, especially if the number of classes are fewer. From the image on the left, we can see that across 5 trained model instances on slightly different hyperparameter settings, A and C, which corresponds to ABN, shows very unstable finicky activations, while B and D, which corresponds to LFI-CAM, shows very consistent, stable attention maps. Additionally, SCORE-CAM achieves better visual performance than conventional gradient-based approaches, but multiple forward computing makes the generation of visual explanation very slow, which our model effectively resolves. Hence, our proposed LFI-CAM is as follows. The general structure is composed of the perception branch and the attention branch. The perception branch extracts feature maps by passing the input image through multiple convolutional layers and predicts a class through the attention mechanism, where the attention map is overlapped onto the feature maps from the intermediate convolutional layer. The attention mechanism helps the attention map improve classification performance by highlighting regions with a higher value of activation while preventing the lower value region from degrading to 0. Meanwhile, the product between the feature maps and downsampled grayscaled input is fed into the attention branch. The main reason ABN produces unstable attention map is because it directly learns the CAM without additional constraints that reflect feature importance. Hence, we replaced the original attention branch with a new network structure called Feature Importance Network, aka FIN. In this new architecture, attention map is generated by the weighted sum of the feature maps from the last convolutional layer and a learned feature importance vector. In our experiments, we evaluated LFI-CAM using 5 different public datasets, CIFAR 10, 100, STL10, Cat and Dog, and ImageNet, and you can find the detailed experiment settings in our paper. We evaluated the classification accuracy on various datasets, and it is shown that LFI-CAM is on par with ABN in terms of classification accuracy for each backbone model, even with less model parameters. In terms of visual explanation, we qualitatively compared the visual explanation generated by 5 models, namely CAM, RedCam, RedCam++, SCORE-CAM, and ABN. As can be seen from this figure, our method shows high-quality results beyond equivalence compared to CAM variant methods, especially demonstrating less noisy and more focused results on both single and multiple target object recognition. To evaluate the effectiveness of the proposed feature importance network, we visualized the pixelized mean feature map from the last convolutional layer of the LFI-CAM, trained without and with the FIN. As shown in the figure, after the FIN's feature importance is incorporated, our LFI-CAM successfully focuses on the most distinguishable region of the target object, where in this example, the steel structure is more highlighted prominently after applying the FIN. Furthermore, as shown in the figure on the right, you can visually see that LFI-CAM shows stable visual explanatory performance in contrast to ABN. To compare the stability of visual explanation quantitatively, we trained 6 model instances with slightly different hyperparameters and chose one model with the highest classification accuracy as a baseline. Then we compared the IOU between the visual explanation generated from the other 5 models with this baseline and plotted them out. We used 127 as activation threshold value, and as you can see from A, LFI-CAM shows that 60% or more overlap happened on average, while for ABN, the overlap is only around 30%. In sum, the LFI-CAM is on par with ABN in terms of classification accuracy and outmatches ABN in terms of attention map quality. This is the end of the presentation, and thank you for listening in.